Alright, boys and girls, welcome back to the drive-through. We're going to start doing some applications of vectors, which is really the only reason they exist. Okay, vectors are meant to represent often forces, anything that has size and direction, or magnitude and direction. But it's really important you understand that the vectors don't have a position. So that vector there is the same thing as that vector here. All that matters is how long they are and what direction they are pointing in. And we're going to have to use that in order to figure out how to orientate some of these things, okay? How to put them in the proper direction. But first, let's just look at adding vectors. What the heck does that give us? So if V is right 3 and then up 4, V could look something like this. Now remember, they don't have a position. So if we put n at left 6 down 1, left 6 and down 1. No, left 6 and up 1, you idiot. God dang it, I'm such an idiot. I can't make these videos much longer. Okay, so there we go. There's n. Now, V plus n. I know you know what that is. I think I know what you did. But what does it mean? Well, what if we went to the end of V and then added n to the end of that? Oh, it's starting to look like a parallelogram. Well, the destination would be right here. And I'll tell you right now, that green vector is V plus n. Watch. Let's add them and see what happens. 3 plus negative 6 is negative 3. 4 plus 1 is 5. And indeed, that vector looks like it's negative 3 and up 5. Okay? So, when we add vectors, the result is going to be called the resultant vector. And there's a lot of geometry to like how to understand and comprehend this. So let's take a look at a real life example. You got this big old tanker boat, okay, and it's being pushed by two smaller but stronger tugboats. Notice the tugboats can't push it in like the perfect or the optimal direction, because they would hit each other. So they have to be at a 20-degree angle. So we'll call this tugboat 1. And this will be tugboat 2. Both of these have 500 pounds of force. Okay, so what are the orientations of T1 and T2? And then what are the results? How much force are they going to push, and what's the total going to be? Well, I hope you're someone that's like, well, since they're both coming in at 20-degree angles, I bet they will push it horizontally. And I think you're right if I do this correct. So let me think about some things real quick. If I put an axis, this here is it's going in this direction, and it says 20 degrees from the horizontal. So that is going to be what T1 looks like on the coordinate plane if it started at the origin, okay? And this is so weird because these things are about ready to flip upside down. Now, T2, on the other hand, is 20 degrees, but it's going right and up. So that one is 20 degrees above the horizontal. Now, it doesn't exactly matter which one you call T1 or T2 because they both are symmetric, okay? But what we have to do is come up with what we call direction angles. So the direction angle for T2, that's in the first quadrant, that's just going to be 20 degrees. So we can say that T2 is 500. Remember that cosines are your x values. So 500 times the cosine of 20 comma 500 times the sine of 20. Now, what is our direction angle going to be for T1? Well, T1 is in the bottom right quadrant, the fourth quadrant, and there's only 20 degrees left. So then T1, the direction angle for T1 must be 340 degrees, 20 degrees less than an entire circle. And it's still a force of 500. Now, let's see where this takes us. So, I think the easiest way to do this math, what we're trying to do, is add T1 and T2. T1 and T2 are both pushing against this tanker. So the sum of their forces will be the resultant force, which is going to be that green arrow. Okay? What I do is I just do all of the work in my calculator. So let's make sure I'm in degrees. I am. And so then what I'm doing is I'm adding the x coordinates. So I'm going to do 500 cosine of 20 plus 500 cosine of 340. And that's going to give me 939.7. Oh, no, no, no. Okay. And then, here I'm just screwing this up, but compared to the other videos, this is just a mild screw up. 500 sine of 20 plus 500 sine of 340. Now, I'm really hoping this comes up to be 0. Boom! Yes! Now what just happened? Well, look, some of our force was going in the downward direction, but the exact same amount it was going in the upwards direction, so there ends up being no y or no j component to this. So, what is the direction? Well, the direction is 0 degrees. It's completely horizontal to the right. What is the magnitude? Well, that would be the square root of 939.7 squared plus 0 squared. But of course, I'm not going to do that. The direction is 939 pounds. And so this is why you bring 2 tugboats. Now you might be like, well, a boat weighs way more than 939 pounds. I know, but that's not how much force it takes to move the boat, because it's on water and there's this thing called friction, and water reduces it. So actually that would be enough probably to push a tanker. Tugboats are the bomb. You should look into them. Tugboat drivers make a ton of money, but they also have dangerous, or risky at least, jobs. Alright, here we go. Now this is like a total homework problem, or a quiz problem if you're more into that. So an airplane is traveling at a fixed altitude with a negligible wind factor. The plane is headed, now you're going to screw this up, 30 degrees west of north. So let's put that on our axis right away. Well, where's north? It's here. And where's west? It's here. So how far is 30 degrees west of north? It's this right here. That's 30, that's 60, this is 90. So what is our direction angle? Well, it's 120 degrees. It's either 60 less than 180 or it's 30 more than 90, however you want to interpret it. And we're going, there's that number again, 500 miles per hour. Now, it's encountering wind. Hey, yay, yay for construction. It's encountering wind at 70 miles per hour, 45 degrees east of north. So there's north. The wind is much smaller. It's only 70 miles per hour. Now, remember what we said. The direction angles, or the vectors, the vectors can exist anywhere. So what is our resultant vector going to look like? That's what it's going to look like. So we need to add the green to the blue, and the red will tell us where we actually go. So what's the red one? Well, we said that this was 45 degrees. So the red one is 70 cosine of 45, comma 70, excuse me, the blue one, 70 sine of 45. Okay, the green one is 500 cosine of 120. We've got to use that direction angle, comma 500 sine of 120. Now we're going to add these up again, just right in our calculator. So 70 cosine of 45 plus 500 cosine of 120, and you get negative, where'd it go? Which way did it go? 200.5. Okay, that's the x. I should have put that in red, and I'm going to negative 200.5. Okay, now let's add the y coordinates. So we've got 70 sine 45 plus 500 sine of 120 and you get 482.5 for that one. Does that make does that look like an answer that makes sense? I think so. Left 200, up 482. Yeah, I buy that. I buy that. I buy that. So, what are the resultant force and speed of the plane? Well, this is the resultant force. The speed is just the magnitude of that. Okay? So, the speed is the square root of 200.5 squared plus 482.5 squared. So we'll go back into this. Second square root, that squared plus that squared. The negative will get canceled by the square, and you get the speed is 438.8 miles. I'm sorry, that's miles per hour. Okay, so let's see. No, can't be. There must have been a little negative error there. So 200.5 squared plus 482.5 squared. There you go, 522.5. That makes more sense. How did I catch that? Well, I knew it had to be more than 500 because we've got some of this wind is in the back. You know, some of the blue arrow is going in the direction of the green because it's going up. How much? About 22.5 miles per hour of it is. Now, what if they wanted you to find the angle? Well, for the angle, what I would recommend is resketch only the red one, okay? And then make it into a right triangle. So here's my right angle. This is 200.5 to the left. This is 482.5 up. So we got opposite, adjacent. Let's just find this angle using the tangent. Now that's not the angle we're looking for, but that's the angle we can find. Tangent of theta is 482.5. Opposite divided by 200.5. Adjacent. How do I get rid of tangent? I take the tangent inverse of both sides. And you get theta is second tangent 482.5 divided by 200.5. So this angle right here is 87.5. Okay, this is 87.5. So how would we answer the direction? You might say that it's 2.5 degrees west of north, or you can say that it has a direction angle of, well, 2.5 plus 90, so 92.5 degrees. I hope that helps. Boom!